Good morning, chemistry fans. We're back. It's Tuesday. It seems like forever since we had some planning days on Friday and Monday to get ready for the rest of the year. Anyhow, let's have a little chat. This week we want to wrap up because of the shift in having Friday and Monday as planning days and having you just kind of use them as cleanup days. A couple of things. Number one, we'll wrap up equilibrium, the whole reaction rate equilibrium unit this week. We have a lab to do. We have some discussion to do, some practice, and a lab to do. And then we'll have an exam at some point next week, but I'm looking at days and trying to figure things out. And then probably going to incorporate some regular cleanup days, maybe once a week. The school's having some that they're calling lightning days. As chemistry folks, we discussed having some just as stopgaps during the week so that people who have had internet troubles, this, that, whatever other reason you can think of, might have the opportunity to clean up. I will say this, I'm proud of all of you in that our drop-off of being engaged in chemistry has been minimal. In fact, I'm very pleased with many of you that you've done better online in getting things turned in on time, etc., than you have when we were in the classroom. Either way, doesn't matter. Whatever works, don't care. Just thank you all for being engaged in working through this. When last we talked, we set up reactions as far as reversible reactions, and we said that reactions had two opportunities. They can do what we've really kind of been used to all year, kind of talked about all year, that they can go to completion, which means that you put the reactants together, they're just doing their thing, the limiting reactant runs out and it all stops. The other option is that it can go achieve equilibrium, which means it's a reversible reaction, like the multi-billion-dollar ammonia reaction, which we're going to see, in which case then, at a certain point after you put in the reactants and you're making products, the products then circle right back and make the reactants. And so you get into this when the forward reaction and the reverse reaction are equal, you get into this dynamic equilibrium state where the concentrations of the substances aren't changing, even though the reaction still occurs and cycles and things break apart and go together and break apart. The amounts of each aren't, because they're happening at the same level. And our question then is, what can I do to throw something out of equilibrium, which is the whole point of, as we introduced, Chatelier's principle. If a system at equilibrium is stressed, the system will shift to relieve the stress and reestablish equilibrium. And that equilibrium may not be in the same exact spot. It may not be exactly, whatever, like when we're talking with chemical reaction. When it gets to equilibrium, and we showed you how to do the equilibrium, one's kind of the dividing line. If my number is less than 1, then I got to equilibrium when I had more reactants than I did products. If I got to equilibrium after 1, then I had more products and reactants. And if I'm selling stuff like ammonia, I don't want to just be over 1. I want to be towards infinity and beyond and have as much stuff as I can. And so if my ammonia reaction, which when it comes to equilibrium doesn't have a viable quantity of ammonia to sell, then can I do something to shift that equilibrium and push it more towards where I have almost all product and very little reactant? And that's what you can do, and that's what Chatelier figured out, and that's the situations we're going to talk about and what your lab's going to be. And so the question is, number one, how do you stress a reaction in equilibrium? And think of it like our little diagram here is a seesaw, a teeter-totter, that equilibrium is kind of being in balance, even if it's not exactly straight across. But then what you're doing is causing a little change in that seesaw, and it finds a new balance. The other thing, as we jokingly say in chemistry, is this is where you need to know your shift. Careful how you say that. And the shift is it shifting right towards the products and creating more product, or is it shifting left back towards the reactants and creating more reactants? before when it established a new equilibrium. So let's just jump in and get going, and you'll see. And then tomorrow we'll just have kind of a examples, a little bit of homework examples, and then Thursday, Friday will be the lab. You know, Thursday we'll do it, Friday we'll talk about the analysis. And then we'll, at a point next week, we'll have your assessment and move into acids and base. Anyhow, so here what I have here, one stress you can do is change the concentration of one of the substances. Now, here's our multi-billion-dollar equation. I could change the concentration of nitrogen or hydrogen or both or ammonia, okay? Any of the above, I can change. So that's a stressor. You know, it's in equilibrium and all of a sudden I add in or I remove concentration, okay? So concentration can be increasing or decreasing. And again, for all the stressors that we are walking through in here, the question is, will the equilibrium shift towards reactants, left towards the reactants, right towards the products, or maybe not shift at all? And then think of it as seesaw. So here, instead of having our whole equation, I just said, here we have reactants A and B, and here we have C and D, and we're pretending it's an equilibrium on a seesaw. It's even straight across, okay? Now, if you increase the concentration of a substance, so for example here, and it's a different color, say after it got to equilibrium, I added in more of substance A. Well, you can see if I add in more A, then the stressor is going to be, I just overloaded that side kind of dropped down, I'm out of equilibrium, okay? The question then is, since I overloaded this side, what's it going to do to relieve the stress? Okay. Now think about collision theory and reaction rate and everything else. I was at equilibrium. Everything was rolling through and it was cycling through and my concentrations weren't changing. And then all of a sudden into the reaction vessel, I threw some more A. Well, in chemistry terms, then I've got more A to collide with more B. And if more A is colliding with more B, then I'm going to, the stress relief is going to be, I've got more A colliding with B, I've overloaded this side. The forward reaction is actually going to move a little faster than the reverse, so it's out of balance. I'm going to make more C and D until it gets back into balance. Okay. And so I started with A and B, I added A, I've got more collisions going here. It threw it out of balance. I'm going to try and get back into balance by creating more C and D. Now, will it be exactly the same straight across? Maybe not necessarily, but you get the idea that if I add a reactant, it's going to shift the equilibrium away from where I added the reactant. So it will make, not four, but it will make more C and D to balance things out, okay? So look up here. In our multi-billion-dollar reaction, I've got nitrogen, hydrogen, and ammonia. It's giving off some heat. It's in equilibrium. Nothing's changing as far as concentrations of nitrogen, hydrogen, ammonia. And then I pump in more nitrogen gas. It's going to shift the equilibrium to make more ammonia. It's going to shift it right towards the products because I overloaded the left side. I got more nitrogen slamming into hydrogen, and it's going to make more ammonia until it resettles back in equilibrium, okay? Same thing if I added hydrogen. I'm going to overload this side, bam, 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 okay? And I'm going to make more ammonia till it rebalances out. So any addition to the reactant side of either of these, increasing the concentration of either or both of these, is going to shift the equilibrium more towards the product side as it relieves the stress of being overloaded here. Same thing for ammonia. Say I'm making this ammonia and I pump some ammonia back in. Well, that's going to start interacting with the heat to go back towards the reactant. So if I added, okay, ammonia here, if I added in more ammonia, then it's going to shift the equilibrium back towards the reactant side, okay? So if you increase the concentration of a substance, the equilibrium will shift away from the increased concentration. So added reactant will shift right, added product will shift left. Okay. So here, if I add an A, it's going to shift right to make more C and D. If I add in D, it's going to shift left to make more A and B, and that kind of idea. So then the question is, what if it decreases? What if I take that substance away? Like in the ammonia equation. As soon as this ammonia is being made, I'm going to have a gas pipe that is piping this out of the reaction vessel so I can sell it off. So I'm removing that away. Okay. So let's look at a general example. What happens if I decrease the amount of D? So A and B was making C and D, and I was in equilibrium, but then all of a sudden I started taking D away. Okay. Maybe it was a precipitate, so I started filtering off the precipitate, pulling it away. It may have fallen down as a solid, and I can just, it can just fall out, be messed through, or something along that line. We can make up what we want. Well, D's gone. C's got nothing to react with. I've thrown it out of balance. A and B need to have a little moment where this reaction is going faster to replace the D than this reaction is going back to stay in equilibrium. And so what I'm going to do is I'm going to make more C and D and bring the equilibrium back. Okay. So my teeter-totter is a little goofy, but there you go. So if I decrease, if I pull away a reactant, then the equilibrium is going to shift to replace it because it's missing. Okay, so it's going to shift left. If I remove, like in this case, the product, D, then the equilibrium is going to shift to the right to replace the missing D. So if I add concentration, it shifts away from where I added the concentration to the other side of the reaction to get back into equilibrium and balance it back out. If I remove something, then it's going to shift towards what I removed to get it back into balance and replace what was missing. Okay. Another stressor you can do is temperature. Okay. You can increase the heat or cool it down. Okay. Now, it depends on whether it's exothermic or endothermic, because exothermic reactions, you have heat, quote unquote heat, energy written on the product side because it's released, as we talked about last time. If it's endothermic, you can see the word heat is written on the reactant side because you need that heat to get A and B going to make C and D. Okay. So one, it depends on whether you're exothermic or endothermic. You have to know which side the heat is on. Okay. Then it really is treating heat like concentration. Consider the word heat just like any of the other substance product things. It's really a concentration thing. Okay. Okay. And here's our exothermic, endothermic. If I increase the heat in an exothermic reaction, that's the same as loading up on a bunch of heat on this side. So it's going to shift the equilibrium back. A lot more heat is going to be working with C and D. It's going to shift it towards the left, towards the reactant side. And the equilibrium will shift in that direction towards the left. If I cool this down, if I have this in an ice bath, and the heat dissipates as this reaction is going, then it's going to shift the equilibrium to replace the missing heat. And so it's going to shift it to the right. Endothermic, again, if I increase the heat, I've overloaded this left side. It needs to shift. It's going to more, A and B are going to be colliding more, making more C and D. The equilibrium is going to shift away from the heat to this product side. If I'm cooling this down, then I'm going to be losing that heat. It's not colliding as much. I'm going to overload this side. It's going to shift to replace the heat. So temperature is just like concentration. If I increase the temperature, it's going to shift away from whichever side the heat is on. Okay, exothermic reactions will shift left. Endothermic reactions will shift right. If I cool it down, then it's got to replace the missing heat, so it's going to shift towards the side that has the heat. So exothermic would shift right towards the heat if I was cooling it down. And endothermic would shift left towards the heat if I was cooling it down. Okay? So you can think of temperature changes the same way you would think of concentration if you just imagine heat as a substance and just not as an energy. Okay? The last thing we can, so here we go, sorry. Let's talk about our multi-billion-dollar equation. This is an exothermic reaction. Nitrogen and hydrogen combine to make ammonia and release heat. If I were to increase the temperature here, then the heat's going to combine with the ammonia and shift away from the heat, because that's like adding heat, shift away, and I'm going to make more nitrogen and hydrogen. Okay? If I were to cool down this reaction vessel, then the heat's going to go missing. So the nitrogen and hydrogen are going to work harder and create more heat because they're going to make more ammonia to replace the missing heat. All right. So here's what they do. They have ammonia production at around 99% product, 1% reactant. It's reversible. So it gets in equilibrium, and then they keep it shifted basically into a high state of kind of disorder, to a regular state of disorder, imbalance, very close to the 98% ammonia production area. How do they do that? Well, it gets in equilibrium. This occurs in one big reaction vessel. Nitrogen is piped through some pipes from another container. They're all gases. It's piped in to the vessel. Hydrogen piped in from another vessel. The two combine and produce heat. Okay. Once they get in equilibrium, they add more nitrogen into the nitrogen container. They just keep adding it. They just keep adding hydrogen in the hydrogen container. So you're increasing the concentration, shifting the equilibrium to continually make more ammonia. Okay. They also then at that time are draining the ammonia through a valve out of that container. So it's like decreasing concentration. So again, it keeps driving nitrogen and hydrogen to make more ammonia. And then this reaction that it's occurring in, they cool it down. So it's as if so the heat is disappearing. So again, it keeps shifting towards making more ammonia because you're messing with the temperature and you're driving it to make more product. Okay. So that's a real example of how they do stuff. Now we have one more stressor to discuss. Okay. And that is, and I want you to pay attention again to the phase symbols at the bottom. And in our multi-billion-dollar reaction, they're all gas, G. Okay. So our next thing, here's what we've learned. Concentration change is a stress that will alter equilibrium. Temperature change is also a stress that will alter equilibrium. And they work very similar. In fact, exactly the same, as long as you think of heat as a substance. The final stressor only affects gases, and two things you have to pay attention to. What are the coefficients of gases? Now, this one happens to be all gas, but you know some reactions will have solids and liquids and whatever. So you have to pay attention to the small letter to see what phase am I in. Gases only count. You also have to look for the coefficient, because the key to this is going to be counting the number of moles of gas on each side of the equation. So how many moles of reactant do we have in gas? How many moles of product do we have in gas? And then we have to think about products of gases like we learned in the gas phase area. Okay. Gases love to spread out. So the bigger the volume, the more they can spread out, the farther they can get away from each other. That is much preferred. And they also would be in what's called entropy, much more disorganized. So in this equation, much more disorganized means on this side I have nitrogen and hydrogen. On this side I only have one substance. More disorganized means more separate, different compounds. Okay. All right. Other things to remind you of gas laws. If you think back to the gas laws, only a gas can be compressed. Therefore, those pressure changes or pressure volume changes, because as you change pressure, you always change volume. can be a stressor. And in a sense, it's kind of like concentration, because if you think back to when we talked about gas laws, shrinking the volume is increasing the concentration and stuff, because you're just putting more of those particles, more of those gas particles are now in a smaller area. Okay. So reminders of Boyle's law: increasing or decreasing in pressure will change the volume, right? Increase in pressure, decrease in volume, because they were opposites. They were inverse relationship. Decrease in pressure, increase in volume. Okay. So because of that, any change in pressure will create a change in volume, which will shift the equilibrium based on the number of moles of gas you have in the reaction. All right. This is one that's easier to work through looking at an example. All right. So here's our multi-billion-dollar reaction. We have 1 mole of nitrogen plus 3 moles of hydrogen is 4 moles on this side. We have 2 moles of ammonia on this side. The heat is irrelevant. And I say that looking at the fact that they're all gases. If there was something here that wasn't a gas, I wouldn't count its moles. And we're just going to use the flat line teeter-totter to say, okay, we're in equilibrium. We have 4 moles here on this side, 2 moles on this side. Okay. What happens if we increase the pressure in the reaction? Well, remember, an increase in pressure is a decrease in volume. So the side that has more moles is going to be more stressed because you're jamming more particles into a smaller area, right? So I'm stressing the 4 mole side. So the equilibrium is going to shift to balance out. It's going to shift towards the 2 mole side. Okay. So in our reaction here, an increase in pressure is going to decrease the volume. It's going to shift the equilibrium away from the reactant side to the smaller mole ammonia side. Okay. Because again, the gases don't want to be compressed and don't want to be, so the least moles I can have in that area, the best. Okay. So increase in pressure shifts the equilibrium to the side that has the least moles of gas. Okay. What about the opposite? What if I decrease the pressure? And so a decrease in pressure is an increase in volume. They can spread out more. So really the side with the least moles of gas, the 2 mole side, is more stressed because gases want to be more spread out and have more moles spread out the more they can. So that's going to shift the equilibrium to the side with more moles of gas. So the equilibrium will shift to the 4 mole side to balance out, because if I have a bigger volume and I have less pressure, I want to have more moles. I want to spread that gas out. Now the question you might have is, what if they have the same amount of moles on each side? What if you have the same amount of moles of gas on each side? Then you start looking for things like this, where I have 2 substances of gas on this side and 1 substance on this side, and you prefer the one with the higher number of substances. But that's not to be too big a concern. That's really only a concern if the moles of gas are equal. Then you start looking at how many different types of gases you have. Okay? Anyhow, let's do a quick summary, and then tomorrow we'll go work through some homework together. Reactions can be reversible, and when they do so, after a period of time, they come into a dynamic equilibrium, which means that they're making the product at the same rate that the product's breaking down and going back to making reactions. By Le Chatelier's principle, then you can stress that system in equilibrium and shift the equilibrium, either toward more reactants or towards more product. It depends on what you're looking to do. And I have 3 ways I can stress that reaction. Well, I have 2 big ways, and 1 way if there's a gas involved. Any gas, even just 1 gas on one side. What I can do for everything is either increase or decrease the concentration of a substance or multiple substances. An increase in concentration will always shift the equilibrium away from where I added in the extra. So if I add it in the product side, it's going to shift toward the reactant side. If I add it in the reactant side, it's going to shift to the product side. Conversely, I can always decrease the concentration by removing a substance as it's being made, or as it's, get a leak in the gas tank for the nitrogen and it starts escaping. I don't know. Anyhow, a concentration decrease will always shift the equilibrium towards wherever it went missing, towards the decrease. Temperature is exactly the same. You just have to know which side the heat word is on. If I increase temperature, it's going to shift the equilibrium away from the heat. If I decrease the temperature by cooling it down, it's going to shift the equilibrium towards the heat. And then as we looked at here with the ammonia, if I have a gas, a pressure increase will shift the equilibrium to the side with the least moles of gas. A pressure decrease will shift the equilibrium to the side with the most moles of gas. If both sides have an equal number of moles of gas, then I want to look at which one has more different gas molecules, particles, whatever. Okay. And in all reality, every one of these stressors is what a ammonia making plant does to drive the equilibrium constantly to the product ammonia side. Okay. Anyhow, there we go. That's it for Tuesday. Again, we'll be back again tomorrow to walk through some more examples and do some homework. Until then, just stay safe and have a great day.